Hello and welcome. I appreciate you returning to my channel, especially if you're looking for more information on calculus. In fact, I find self-study to be an incredible driving force. That's why I'm here, self-study. I wanted to start out today. Well, this is going to be Unit 1.1. If I actually have a pen, Unit 1.1. We're going to call this how do we know, or how can we represent a function? Taking you back to your algebra. So, calculus in general studies change, and the way it does that is by modeling change with functions. In fact, it's a very important concept to understand functions, why you're taught them in algebra before you normally will take calculus. So, let's start out by defining what a function is. A function is a rule that assigns each element x in a set D to exactly one output f of x in set E. Now, this is a very complicated definition of a function. But to break it down, what this is really saying is for any value x, there can only be one value f of x that it corresponds to. And this is important for several reasons. More or less, because whenever we're looking at a graph, let's say I have a graph right here, and this is what the graph looks like, okay? But if it were to look like this, and let's say that both of these are on the exact same xy plane, and they're part of the same function, this would be very hard to evaluate at any one value x. And you'll see with calculus, this idea right here won't work at all for us to have two y values for any given x values. So there is several ways we can represent functions. We can represent them as a table of values. For example, we can call this time, and we could call this population. And we could call this time 1, time 2, time 3, 4, time 5. And we could track the population. Let's say it's 100, 200, and so on. This is one way that we can represent a function. Another way we can do it is visually. As I just showed you, we can do a graph. And I'll just do a parabola. We do love our parabolas, and my tablet wanted to make that parabola very strange. Let's try that again. There we go. And this graph might be even more useful since this graph tells us the zeros of our function. That's a thing dealing with the fundamental theorem of algebra. But that is something that is going to come up in calculus as well. And the third way that we can represent a function is algebraically. We have many functions, a lot of functions actually, that deal with algebra. For example, we have our polynomials, which are our x plus xk plus x to the z, let's say. But the difference between a polynomial is they all need to be integers. But I'm going to assume for the most part you understand this concept of what things can be functions. What happened? Oh, for whatever reason I wanted to open that. That's concerning. Oh, good heavens. It happens, so. It happens. Alright. Continuing on. So what does this D up here represent? And I'm going to actually ask a question about it. This D represents the domain of a function, which is also, you can think of it as the input values. Sorry, my tablet has a very strange spot right there, but anyway, I digress. The values that will give real outputs, or really just outputs that would make sense. So I wanted to start out by asking, what would be the domain of x plus 2? Well, we actually do have a way of finding this. We know that x plus 2 must be greater than or equal to 0. So x must be greater than or equal to 2. And this would be the domain of the function. I'm going to go and erase all this, and I'm going to give us another example. In this example, we are going to look at the function 1 over x squared plus x. Now, this function is going to have a different kind of domain restriction. So, as we know, the denominator of a fraction can never be equal to 0. So we never want x squared plus x to be equal to 0. Now let's try to find where it's going to be equal to 0. And we're going to use factoring to do that. So we're going to call this x plus 1. Pretty simple. So, and then if we solve for x, we get x is equal to 0 and negative 1. So our domain is going to be all real numbers, comma, x cannot be equal to 0 or negative 1. Honestly, I'm really liking this pink. Pink is my favorite color, and I wanted to try this, and I definitely think I like this a bit more on a black background. Continuing on, how do we know if a graph is a function on a line? Or on a, yeah, if a graph is a function. So we actually have a test for this. Let's say our function looks like this. And let's give another function that somewhat looks a bit more messy. In fact, I want it to be a hyperbola. I believe that's what this is called, a hyperbola. A hyperbola. And how do we tell if this is a function? Well, as I said earlier, we want only one value of x on each of these axes. So for the first one, let's look at this left from right. Is there any x? No, there's only one, only one, only one, only one, and only one. And this is called the vertical line test. If you draw a straight vertical line up and down, and the function, and it intersects a function at more than one point, or a graph at more than one point, then it's not a function. Now, if you look at this hyperbola, you can draw a straight line, and it does intersect, it does, and it does, so it was not a function. Alright, let's move on. Let's move on to piecewise functions. Piecewise functions. So, these functions are defined or have different rules depending on where they are at in their domain. And the first example I'm going to give you and what this might look like is f of x is equal to the piecewise function. Sorry, this kind of looks a small bit strange. X plus 3, and let's say x squared plus 3 for x is greater than 0 and x is less than 0. And let's just say that's going to be equal to. So, if I wanted to graph this function, we're going to draw out a graph. It's going to go x, and then just call this f of x, or y. Well, we're going to, there's one point that I really care about, and it's going to be at this little 3. So we know our x is increasing, so it's going to look something like this. And then we have a parabola, and so it's going to go up 1 over 1, and it's going to look something like that. And this is useful because sometimes not everything is going to follow a set rule for its entire domain, especially in modeling real life. And that's what we're trying to do. We're trying to build our modeling abilities here. Another really good example of a piecewise function is f of x is equal to absolute value of x. And you might be like, that doesn't look like a piecewise function. But we can actually break this down into a piecewise function where negative x is going to be for x less than 0, and x is going to be for x greater than or equal to 0. Now this, and we can test this, let's say I want to plug in the absolute value of -1, f of -1 is 1. And if I plug it in down here, -1 is less than 0, so we're going to use this top function. -1 times negative is going to make it a positive 1, and we see that it does hold up. And the next topic that I'd like to talk about is even or odd functions. Even or odd functions. I honestly find even and odd functions kind of fascinating. So, a even function is a function where f of negative x is equal to just f of x. It makes evaluating it relatively easy. Or an odd function so then we might be given f of negative x is equal to negative f of x. And why might we want to know this? Well, let's say f of 3 is equal to 5. So then, what would be the value of the function if it's even? It is even. It would be 5. Or what if it's odd? It would be -5. How do we know if a function is even or odd? Or neither. Well, there's a test we can do. So we're going to define our function f of x to start out. And we're going to call it x to the power of 5 plus x. And if we want to test if it's even or odd, we're going to just say f of -x. So we are going to get -x to the 5th minus x. And now if my algebra serves me right, this is just the same thing as -x to the 5th minus x, which is the same thing as -f of x. So this function here would be odd. All right, let's do another example. Let's do f of x is equal to 1 minus x to the 4th. So let's once again do our little test. F of -x is equal to 1 minus -x to the 4th. And evaluating that, that's just 4 -x squareds multiplied by each other. So that would be 1 minus x to the 4th. So then we see that it's the exact same as the original function, so this would be even. And now, one final example. F of x is equal to 2x minus x squared. So we're going to start again by plugging in a -x, and we get -2x minus x squared. Oh, that's an issue. It's not either even or not odd, so it's going to be neither. And that's also a possibility. On interval I. Okay. The next very fun topic is we're going to be dealing with increasing or decreasing. So, let's see. A function is increasing on an interval. On a interval. And we're going to just define this interval. x1, x2. If f of x1 is less than f of x2, if x1 is less than x2. So, this function right here would, in theory, could look like something like this. And we're just going to call this value right here x1, and this value here x2. Now, this function does indeed decrease in said interval, but on average it is increasing. So it is increasing on the interval from x2 to x1, if that makes sense. a function is decreasing on a interval x1 to x2 if f of x1 is greater than f of x2 if x1 is greater than x2. Let's draw another graph here. And you know what? I want to do it something special, something recognizable, so I'm going to do a sine. So let's see. We're not going to worry about that very wonky amplitude, but let's call this value here x1 and this value here x2. So we can tell that this is very clearly decreasing. All the x values are getting more and more smaller. And that's really what the true definition of a decreasing function. That f of x is getting smaller. And the opposite is f of x is getting bigger. Bigger. Sorry, once again, about my mediocre handwriting. The next subject I would like to talk about is the difference quotient. And you're going to see me put little stars up here by it, because this is a very important idea. In fact, you're going to see it come up later in Chapter 2. The difference quotient. So, what is a secant line? I'm going to start by asking that question. What is a secant line? Well, we're going to call this graph here f of x. And we're going to call this point x1, and this point over here x2. So the secant line is going to be just a point on the graph that connects the two. That is all the secant line is. And this is what the difference quotient is going to give us, a secant line. More or less the slope of said secant line. So, what is this difference quotient? So, what if I want to know the slope closer to this x1? Well, let's just define a new distance here. Let's call this x plus h, or x1 plus h. And we're actually going to just, for the purpose of the difference quotient, we're actually going to call this x. What if we want to know the equation of this? Well, we know that our equation for line is y2 minus y1 is equal to x2 minus x1, and this is equal to our slope. So let's see if we can maybe find a way to put this into our terms of our graph. So this point right here is actually going to be f of x plus h. And because that's further to the right, let's just define that as our secant line, or as our y2. So f of x plus h minus. And right here, we already said this is just going to be f of x right here. So it's going to be minus f of x. Now, let's think, well, what's going to be our x values? We have x or sorry, x plus h minus our original x. So what do we get? We are going to get m is equal to f of x plus h minus f of x all over h. And that, my friends, this right here is the difference quotient. This idea is one of the most important ideas in calculus. But let's do something with this difference quotient. Let's work with it. So, let's see. Let's define a function. F of x is going to be equal to 4 plus 3x minus x squared. And this is right here, my friends, is going to be our f of x, or f of x. How are we going to find our f of x plus h? Oh, a bit like earlier, we can just plug in f of x plus h for our x's. So we get 4 plus, let's see, so we want to do 3 times x plus h minus x plus h squared. So we're going to call this f of x plus h is going to be equal to 4 plus 3x plus 3h minus x squared minus 2xh minus h squared. And now let's plug this back into our original function. So we are going to... So we're going to then take this, and we're going to just call this m is going to be equal to... Ooh, you know what? Actually, scratch that. I need a bit more space, so I think I'm going to do the rest of this calculation on the next page. So we are going to do 4 plus 3x plus 3h minus x squared minus 2xh minus h squared minus our original f of x. So this is going to be minus 4 minus the 3x plus the x squared. And all of that is going to be over h. And this is equal to m. So now let's just look. This will probably get a lot simpler, right? So let's see. We have a 4 there, and we have a negative 4 there, positive 4 there. Cancel them. We got a negative 3x, and we got a 3x. Cancel them. We've got a 3h. I don't think anything cancels that, but we do have an x squared, negative x squared, and an x squared. Cancel them. And you see, we are left with a lot simpler of a figure. In fact, we are only left with h's. And now we can see that our m is going to be equal to 3 minus 2x minus h. Let me double check that I did all that right. I believe I did. And this, my friend, is the power of the quotient, the difference quotient. It gives us the ability to find the slope of the secant lines of a given point. We can plug in whatever value for change in h, or for whatever value for h we want. H, and we can find a slope for a secant line. Or we can plug in whatever value of x we want. For example, if I wanted to know the slope of the secant line of f of x at x is equal to 3, well, we now have the tools. And in fact, I'm just going to say that I was referring to my original f of x that's up here, the one that we just did this quotient, or the quotient different, or the difference quotient, sorry for my stuttering, for. And we would get that m is going to be equal to 3 minus 6 minus h. So m is just going to be negative 3 minus h. And that h can be any difference, really, from the original f of x. And in fact, you're going to get a closer and closer approximation for a slope of maybe a tangent line for f of x as you bring that h closer to 0. Well, anyway, I want to say thank y'all for joining me. I hope you have a wonderful rest of your day, and I hope you found this video informative. Have a wonderful rest of your day.